Hello, Year 13. We're going to be looking at a new topic in today's lesson called Turning Points in Physics. In this topic, we examine key moments in the history of physics, key discoveries, key people who made big leaps forward in our understanding. We're going to look at their experimental work, and we're going to look at what they deduced from the results and how that underpins our modern understanding of physics. So we start with the discovery of the electron by J.J. Thomson in 1897. I should also give credit to William Crookes, who came a bit before J.J. Thomson, and he did a lot of the groundwork as well. So we're going to give him credit. He played a part in this journey, as did many other scientists, in the discovery of the electron. Here are the key learning outcomes. So we're going to know the relevance of the production of cathode rays in a discharge tube. We will be able to explain the principle of thermionic emission and its use. We will know how to determine the specific charge of an electron and significance of Thomson's determination. So we start in the 1870s with William Crookes. He did experiments. He was a chemist. He did experiments by putting different low pressure gases in glass tubes and passing a high voltage across the tube. So we're talking thousands of volts here. He noticed that if you put different gases in these tubes, that you got different colors, which obviously you can imagine caused a great deal of interest. There has to be a low pressure gas. Okay, we'll come on to the reasons for that. If it's a high pressure gas, it doesn't work, only works with low pressure gases. He did experiments. He put things in the tubes, and you can see at the bottom there a Maltese cross. And that also was significant and aided our discovery of the electron. So let's move on. Now, the Maltese cross is this metal shape. It looks like a cross. It becomes the anode, and the cathode there is at the end. The whole tube glows when there's a high voltage between anode and cathode. However, what's interesting with this result is that we get a shadow at one end, and this showed Crookes and Thompson that whatever is happening inside the tube, it must be coming from the cathode. So they said that there must be cathode rays, something coming from the cathode, similar to light rays in some ways, because we get a clear, sharp shadow. So these cathode rays travel in straight lines, and they come from the cathode. We now know, of course, that these are electrons, but at the time they didn't know that. So this is just a close-up of Crookes' tube. It's also called a discharge tube. It has gas at low pressure. You can put different gases inside the tube, even air. You get a glow with air, a green glow. There's a cathode at one end, which is negatively charged, an anode at the other end, which is positively charged. And we need a high voltage across the plates between 5,000 and 100,000 volts. There is a pump which sucks out the air, and it's low pressure air. It's not a vacuum, but it is low pressure. So Crooks and Thompson did experiments with these discharge tubes. We can see at the top here, we've got a tube which has now got a paddle wheel inside of it. The paddle wheel is able to move in that gap there in the middle. If I can get my pen to work. Here's the paddle wheel, and it can move across like that. So if we have the cathode at this end, here's the cathode, the negative, and the anode at the other end. When they put the high voltage across the electrodes, they found that this paddle wheel starts to rotate. Okay, I'm not quite sure which way it rotates. It starts to rotate, and then it moves across the tube like that. And what that told Crooks and Thompson was that cathode rays transfer energy, mass, and momentum. So it looked like they were particles of some kind. Now you can watch a video of this if you click this link. I will put this PowerPoint into its learning, and you can click on that. There's a video, just a short clip that shows this experiment. Another experiment involved at the bottom here using a magnet, and you can see in this tube you can actually see the cathode ray tube. This gas is glowing green, it's probably air, and the experimenter is moving a magnet, and this causes deflection. And if you change the polarity of the magnet, it changes the direction of deflection, and that told Crooks and Thompson that we were probably dealing with negative charges. Okay, so we know it's a particle, we know it's a negatively charged particle. How do we know it's negative? Because if you apply Fleming's left-hand rule to this, the deflection is caused by a moving negative charge. Okay, if it was a positive charge, it would deflect in the opposite direction. Now the gas in the tube, as we've mentioned, glows. In fact, it glows in two different places, and you need to understand what causes the glow. So looking at this tube at the top here, we have a picture. We have what we call the positive column in here. There's a positive sign in there and a negative sign there. That's called the negative glow, and the other one is called the positive glow. The anode is at this end and the cathode is at this end. So let's talk about the negative glow first. And at the bottom here, I've got a detailed explanation which you can read in your own time more slowly. I'm going to quickly go through it. The emission of light from a discharge tube happens because the voltage applied to the tube is so high that some of the gas atoms in the tube are ionized. So what's happening in the tube here, we've got atoms where ionization is occurring. So we've got positive ions and we've got negative electrons. We know that now, of course. And we know that the positive ions go that way and the electrons go that way. So we've got ionization, separation out of positive and negative charges, because the electric field is very intense and it pulls the electrons out of the atoms. Positive ions created near the cathode are attracted to the cathode surface, causing free electrons from the cathode surface to be emitted. So this ion slams into the cathode and we get negatives here being emitted. As it slams into the cathode, negative electrons are emitted. Okay, these electrons are accelerated towards the anode and collide with gas atoms, causing them to be ionized. The glowing gas near the cathode, the negative glow, is due to photons emitted when some of the positive ions and electrons produced by ionization recombine. At the other end, we've got these negative electrons were separated out in the ionization. Some of the electrons pulled out of the gas atoms do not recombine and are attracted to the anode and therefore move away from the cathode. Hence the term cathode ray was used to describe them. These electrons move towards the anode, cause excitation by collision of gas atoms in the tube. The positive column of glowing gas is due to de-excitation of these excited gas atoms. The processes of recombination and de-excitation result in the emission of photons of visible and ultraviolet light. So please read through that again yourself. Make sure that you understand what's going on. So these experiments and others, which I'll move on to in a minute, led Thompson to hypothesize that cathode rays must be negatively charged particles because the cathode rays transfer energy, momentum, that should be momentum, mass and charge. He proposed that cathode rays were composed of a new subatomic particle called the electron. He was duly awarded the Nobel Prize for Physics in 1906. Now, our second learning point was thermionic emission. Crookes tubes did not, the electrons that came off the plate were because ionization and the positive ion slammed into the cathode, which caused it to release electrons. Now, in modern tubes, we use something called thermionic emission. Most modern cathode ray tubes have hot cathodes, so that cathode rays, electrons, are liberated by a process of thermionic emission. So what we do in a modern tube, We have some of these in school. I'd love to show you them. I might try and post a video of this if I find one on the internet. Is we heat up the cathode. We pass a current through the cathode that heats up the cathode, and that causes the liberation of electrons from the surface. That's because we've supplied enough thermal energy, right? We've supplied enough thermal energy to give these electrons enough energy to overcome the work function of the material. And you'll remember the photoelectric effect, that in order for the electrons to be liberated, we had to have an energy bigger than the work function. So thermionic emission is not the photoelectric effect, but there are some similarities. Okay, so make sure that you read this and understand it. So here is a modern cathode ray, and this is something which we've developed, and this is the hot cathode. Here's the hot cathode. It has a heater inside of it, which needs a low voltage, okay, 6.3 volts here. That heats up the cathode, and that causes electrons to be emitted from the surface of the cathode, and they are accelerated towards the anode over here. So this metal thing is negative, it's the cathode, and this one over here is positive. There is a hole in the middle of the anode, which the electrons or the cathode ray particles can travel through. You'll notice that the electric field lines are going back towards the cathode. Remember that electric field lines show the direction of a positive charge. Now, I'm going to introduce a little bit of maths now. We say that the electric field does work on the electrons, and the equation that we use is work done equals charge times voltage. Okay, we have done this before in the electric fields topic, so I hope you're familiar with that. E is the charge of the electron, B is the voltage between cathode and anode. The electric field does work on the electrons, and the electrons accelerate and gain kinetic energy. And they gain energy here. We've got the formula, kinetic energy equals 1/2 times m times v squared. So we can equate those two. We can say that EV equals 1/2 mv squared, because the work done by the field equals the gain in kinetic energy. And if we rearrange that, we can find an expression for the final speed of the electron. There is a question on the paper that I've attached to today's lesson which asks you to work out the final speed of the electrons as they whiz through the anode. So you would use that formula, that key bit of physics here, where the work done by the electric field on the electron equals the gain in kinetic energy. Okay, let's move on. Now, J.J. Thompson, he took Crookes' experiments a stage further. So he's got the cathode at this end. Here's the cathode, here's the anode with a pinhole in the middle, and that allows the cathode rays to pass through. Now, he applied two types of field. He applied an electric field vertically, and the field lines go like that. Okay, so the electric field goes down in this case. He also applied a magnetic field, and that goes from north to south, so we had magnetic field lines going across like that. So we've got two fields interacting with each other. We've got an electric field going up and down, and we've got a magnetic field going across. Now, what he did, let's move on, was that he adjusted these fields such that the force on the particle balanced. Okay, so if I have an electron, now we know he didn't know it was an electron. I'm trying to draw one. Okay, there's an electron. Basically, the force is needed to balance. Okay, so if we look at the negative electron there, would have been attracted, moved downwards, and that would have had a force of E on it. Okay, remember that the force on the electron in an electric field is equal to the charge times the electric field strength, and the magnetic force would have been upwards. F equals BeV. Again, that comes from the magnetic field topic, and these two forces would have balanced each other perfectly such that the cathode ray here, which we now know is an electron beam, passed straight through undeflected. So we've got the magnetic force and the electric force equaling each other. And if we do that, we get an expression for the velocity of the electrons as they hit the screen, which is equal to the electric field strength divided by the magnetic field strength. So this is a neat little result, and it basically tells us that the velocity of the electrons just depends on the electric field strength divided by the magnetic field strength. Okay, obviously all in SI units. Right, so let's move on. So that was the first part of J.J. Thomson's experiment. What he did then was to take out the magnetic field, take out the electric field. Okay, so he removed, let's make that clear, remove, it's not writing very well, is it? Remove E and B fields and just accelerate electron from cathode to anode. Sorry, it's not very clear. This is going well. We've sort of discussed this already. The work done by the electric field equals the gain in kinetic energy. EV equals a half mv squared. Rearrange that. E over m equals v squared over 2v. Now this quantity, E over m, you may remember is called the specific charge of the electron. Specific charge of electron. And that equals v squared over 2v. And we can get v because v is equal to E over b. So v squared is E squared over b squared. Substitute that in, and we get the next expression, E over m. The specific charge of the electron equals E squared over 2v b squared. We can measure the electric field strength, we can measure the magnetic field strength, we can measure the voltage, and we can determine what the specific charge of the electron is, and it's equal to 1.7 times 10 to the 11 coulombs per kilogram. Now, this was the first stage in discovering the properties of the electron. They couldn't discover the charge of the electron at first. As far as they got was to get the specific charge, which is E over m. They had to wait for another scientist to come along to get the charge of the electron, and we'll discuss that in a later lesson. So the specific charge of the electron, Thomson calculated that the specific charge of a cathode ray particle, or an electron as we now know it, is 1,840 times greater than a hydrogen ion. Thomson did not think that cathode ray particles had a greater charge than hydrogen ions, otherwise this would have shown up in other experiments, e.g. electrolysis. This meant that cathode ray particles must be the same charge as hydrogen and therefore 1,840 times smaller, less massive than hydrogen ions. Since all gases produce cathode rays with the same specific charge, Thomson concluded that these particles are subatomic and they are found in every atom. So that was the significance of Thomson's discovery. So we've covered a lot there. You might want to watch this more than once to get your head around it. There's also plenty of material online to try and explain this to you. Okay, so please go through the key points of this again if you need to. Have a go at the questions that I've posted on It's Learning. Okay, good luck. Thank you very much for listening.